February 12th. This is called 1.1/1.2. These two sections are small enough we can do them both on the same day. Hopefully, it's a lot of review, actually. A lot of stuff you've seen before, but we'll get started to our first chapter with this, representing linear relations and solving linear equations. Our goal for the day, our learning goal. Oh, I'm still on the color gold. No, blue. Blue's better for this lesson. Blue. There we go. Ooh, another little blue dot there. What's going on there? Get that out of there. Thank you. Ready? Are we ready? I'm ready. Use different methods to represent linear equations. Don't let that scare you. Lots of times learning goals in math are weird because at the start of the lesson, they should almost be at the end of the lesson. At the start of the lesson, I don't know what you're going to talk about, but that's what our goal is. At some point during the lesson today, we want to see different methods to represent linear equations and connect a solution to graphs and equations. Completely mysterious at the start. That's what I'm up to today. Okay, recall. Independent variable. This is a very difficult definition to describe what an independent variable is. And I will get a little AP sidetracked in this because there's a much bigger picture than we've implied so far. So let's take the small version of this. We'll take the small version of independent-dependent, and then I'll make a physical move up here to jump outside of those limitations and talk about the big picture. In science classes and in early math classes, here's what we're going to act like is true. The independent variable, the variable we don't affect. And by affect, what I mean is we're not doing anything with that one. Now, hang on, AP people, because I'm going to say something in a few minutes. I'm going to change it. Time is the ultimate independent variable. Time just goes. When I look up at the clock there, time just goes. If I'm dancing around here, doing whatever, taking readings in the chemistry class, time just goes. That's why it's independent. Nothing I'm doing here is affecting what's going on there. That's mostly true. We certainly act like that's true all the way through high school. And so time is the one to think about. When you really want to think about what's an independent variable, it's the one you can't change. It just does what it does. The dependent variable is the variable that changes based on what the independent variable is doing. See, do you see that's a little bit awkward, that definition. Let's go to chemistry class. Let's say you're got a solution on the Bunsen burner. You're letting it heat up to see what happens. The temperature will depend on the time. After a minute, the temperature of the solution will be higher. See, it depends on how much time has passed. It's dependent. We certainly act like that's the situation all the time, and that is certainly, okay, here we go, the physical move. Now I will step outside of grade 10 math, maybe even up past grade 12 math and really see the bigger picture here and go, yes, scientists definitely make an effort to make sure they set up experiments where they have an independent variable which is not getting changed, and then they look at what the dependent variable is doing. This is very difficult to actually accomplish. It is very difficult to prove things are true. This is why all the stuff with vaccinations and are they safe and are they not went on. It is very difficult to set up a study that actually proves these things are true. I don't want to get all political here, but they achieved it. It's not close. It's not a discussion. They completely proved that vaccines are safe. It is not, but it's difficult to set that up. It's difficult to actually pull that up. I don't want to get distracted by that. What I do want to get distracted by is time. I no longer want to teach time the same way so that you get surprised later by time. I don't know if you heard about this, but if I take my watch and I jump on a spaceship and go really fast, I mean really fast, and I come back and check your watch, our watches will say different things. And it's not because the watches are weird. It's because time works differently depending on how fast you're going. Why does it not matter? Because in normal everyday life, It never affects what you're doing. That is, if I go running really fast down the street and come running really fast back and we check our watches, it'll see the same second. See, it will only have changed by 10 to the negative 8 seconds. It won't have changed enough to matter on anything we're doing. That's why they didn't notice what was happening all the way up to the year 1900. They were like, they didn't know what was happening. It was Einstein who went, I can see what's happening. Actually, that's a bit of an exaggeration. Before that, they had some clue that something was wrong, but they didn't know what was going on. But don't misunderstand. The GPS system only works because we're well aware the satellite's clock works differently than our clock. If that boggles your mind, good. It boggles just about everyone's mind. But I want to mention it now, so when it comes up later, you're not surprised. Back to grade 10. Grade 10, we cannot affect time. We all have the same watch. We all do the same thing. We act like that's true, because it is true until things get moving really fast.
How does the watch know when it moves really fast, and how does it?
Yeah, what a great question. Boy, we could get sidetracked for a week and a half now. No, a year and a half. We could get it sidetracked discussing it. Time is an intrinsic part of the universe. Have you ever heard the phrase space-time? Space and time are connected. It doesn't seem like it. It seems like there's one thing going on, which is me moving around and where I am in the universe. And then there's this other thing going on, which is the time clicking. It's not true. Space and time are intrinsically connected. That is, the time for me right here is different than the time for you over there. We might get the same results, or we might not. How come we don't know? Because the results are so small, the difference are so small that we can't tell the difference between your time and my time. How does the watch know? The watch is measuring how fast time is moving for you. Right there, sitting right there, moving the speed you're moving. It's built in to do that, and mine's to do mine. And we compare for thousands of years, everybody went, see, it's the same. It might not be. But we're certainly going to, back to grade 10, we're certainly going to act like it is, because no experiment we're doing, like you're not going to go to science class at St. John's and start moving electrons around at 99% the speed of light and noticing that they have different times. That's not going to happen. You're going to boil a solution. Perfectly good science, but isn't tripping on the stuff I'm talking about.
Aren't those two smart watches synced to the same world clock?
What's that?
Aren't those two smart watches synced to the same world
Oh, he makes a good point. He's going to go one step past that. Because we're acting like our individual watches are not connected. But the time might not be the same. So, somebody has figured it out. That is, if this is hooked up to a satellite that has a different time than mine, it's figuring it all out and going, oh, you're on the Earth. You're not moving very fast. Here's what your time is. So somebody's done the calculation, or else the GPS system would not work. Really scary stuff. Really scary stuff. And not really part of this lesson, but I only bring it up because I made the statement that independent is the ultimate, time is the ultimate independent variable. And it is, except it isn't. Yeah? But it's the one I think you should use in your examples. When you want to talk about a truly independent variable, time's the one you're going to use most times. Linear relations can be in the following forms. Okay, two different answers to this. Linear relations, here's the way you've seen linear relations so far. Equations. You've seen linear relations given as equations. You've seen linear relations given as graphs. You've seen linear relations given as tables. Or in words. Bob makes $100 per week plus $15 for each table he makes. Does this all ring a bell that you've done a bunch of this? They're supposed to, between grade 8 and grade 9, they're supposed to give you a bunch of this. I make a note, though, that we have also seen that the equations can be in different forms. We may have to shuffle it around to get it actually to be y equals mx plus b. Good so far? Stanley, you cannot possibly offend me what I'm teaching up here. That is, if I move on to a separate slide and you need me to go back, you can just do what you do to your iPad, just reach up and swipe in the air and I'll know what you're talking about and I'll swipe back and we'll get the note. I do not want to rush you in these lessons. I also try not to bore you, so I'm trying to keep them moving. But you just let me know, yeah, as we're moving along. Any questions? All right. For each scenario, define the variables and write two equations. I think you're going to find chapter 1 reasonably straightforward, except for making the equations. That's going to be the hard part. So we start right in with some practice on how to make these equations that define the situations. So it says define variables and then write the two equations. Okay, Provincial Express charges $4 plus $1.50 per kilogram to deliver a package overnight. The package people charge $5 for a package, but only $1 per kilogram. At what amount is Provincial less expensive to use? This chapter is set up to say, I actually won't be able to get the answer yet. For now, I'm only going to build the equations. And there's a worksheet that you'll be able to work on tomorrow where you can practice making these equations. But you might not be able to solve them yet. That'll be the rest of the chapter. Here's the game. The two variables. What two things do we need to know in this situation? What two things might vary in the situation? For instance, when I go to Provincial Express, what possible input will I have? What possible number will I have in my head? And then what possible number will I get back from them? If that helps to understand what I'm going for. What do you need to know about your package to be able to find the cost? What's that? Yeah, how much it weighs, right? So let X be the weight of the package. Those let statements are vitally important, not just from a communication standpoint. Plenty of times in math classes, we'll talk about how important it is to communicate well and to show your form really well. That's true. Way more important than that is these let statements will help guide you in building these equations. So once I know the weight of the package, what am I going to find out using that? What's the real important thing I want to know about this situation? What's that? Yeah, the amount of money. So that's the other let statement. So all through this chapter, we're going to do lots of equations where there's two things in the situation. One that we're going to plug in, the independent one, and then one that we're going to get an answer for, which is the dependent one. And I used x and y, but we'll have some freedom there. We don't have to use x and y. So be the cost. So, Provincial. And I don't know. I think I'll just jump right in and say, can anyone make then the equation for Provincial? And then we'll talk about what we do when it's too difficult to come up with the equation, because it will get difficult to come up with these equations. I hope I've picked one that is familiar from grade 9.
1.5x plus 4.
Well, yes. That's true, only it's not an equation yet.
Equals something.
Equals something, yeah.
Equals
Equals
y.
y. And I don't know where to put the y. Equals y might make more sense in your brain if I put it over here and wrote equals y. But for the sake of going to graph this and do this, if I put the y here, then it's y equals mx plus b, and I'm ready to graph it, which is the first method we'll use to solve these things. Like, what, can we just graph them? The answer is yes. We'll talk about when graphs are advantageous and when they aren't. Now, let's say that was too difficult for you. You're like, what? That's an easy one. I'm like, I know, But I better start now with some strategies on how to handle tougher situations. One strategy is to make a word equation. Most people would understand this word equation, even if their algebra was weak. The cost is $1.50 times the weight plus $4. That is a very powerful mathematical strategy. Is to not try and do any algebra. Go over there and write a sentence that describes what's going on. And from that, then you can make the equation. You go, oh, the cost, that's y. Is, that's the equals. 1.5 times the weight, 1.5x, plus 4. So don't underestimate this. Even if this one was easy for you, don't underestimate writing out a word. A set of words is. I have other strategies coming at you, but that's one of the best ones. So then, package people. Who wants a shot at their equation? After seeing that one, hopefully this one's pretty nice, even if you found it difficult. Yeah, go ahead.
Y equals 1x plus 5.
1x plus 5. Okay. Now, so you don't get confused, some of the homework questions, some of the worksheet for this it asks this question. It says provincial express charges whatever, package charges whatever. At what amount is provincial less expensive to use? And we can't do this yet. That's what I'm going to talk about all the chapter. So this question actually says, for each scenario, define the variables and write the two equations. Done, done. I'm done what the question's actually asking me to do. But it should be out there going, but then how do we get the answer to the question? Oh, that's what we're going to work on. And maybe you've got a strategy, but please don't go too crazy trying to solve these. You can do a couple of them and see if you come up with a way to solve them. But that's what I'm going to teach all this chapter. And the methods I'm going to show can be very, very powerful. So you're better off being a little bit patient here and going, okay, I'm going to do what it says, make the equations. Apparently, we're going to learn a lot about how to actually get these answers. You can do a little bit of it, but don't get carried away. Okay? Any questions about that? All right. More time? Remy earns an hourly wage plus tips. 1 week he worked 12 hours and made a total of $117. The next week he worked 10 hours and earned the same amount in tips as the week before for a total of $110. What is Remy's hourly rate? Again, I'm going to underline this in squigglies. I'm not actually going to get the answer here. I'm going to do what it asks. Define the two variables and make the two equations. What are the two unknowns in the equation? Oftentimes, that's a lot easier than it looks. It's right in the question. It says, what's the hourly rate? Let x equal the hourly rate. And so in this question, let y equal the other unknown in the question, the other thing that we'll be working with it, which is y equal his tips. This is a different type of equation. What would you do? Can anyone do the word equation? If you were Remy or working with Remy, what would you do to find out how much you made? Your tips, yeah. So you take your tips, total money is tips plus, this might be a little difficult. What would you do to figure out the other part of your pay? You got your tips, but you got something else too. Plus your hourly rate. But there's more to it. What do you got to do with your hourly rate to figure out how much money you get? Times hours worked. So this is like your little math playground over here, like, let me just figure out what's going on here, and that's really going to help. Because that is the equal sign. Total money. What's the first one? 117. They gave the total this time. Equals tips. Oh, I don't know what tips is, but I know that's Y. Plus his hourly rate, which I don't know. But how many hours did he work in that first week? 12. I put the 12 afterwards to match up with my word equation, but hopefully what you're actually going to do it right is this. 117 equals y plus 12x. Which goes back to why would you have a general form of the equation? And this is why. Maybe the way the word problem's set up, you're not going to get y equals mx plus b. It'll be your job to make it into y equals mx plus b. How about the second one? The second one, he makes a total of $110. That was made up of his tips plus, how many hours did he work the second week? 10x. So there's the second equation. Notice I'm starting to put boxes around the equations. That's a good math move we're going to use over the next couple of days when we're doing these things, is to put boxes around the important equations. Notice we don't get to find out Remy's hourly rate here, and maybe you would know what to do to get his hourly rate. I hope you would, and that's fine. That's great. I love it. But that's not what this question was asking, even though that's what it says in the question. We're just trying to go, how do we set these up? That's going to be the hard part in this chapter, so we're going to do a lot of practice on it. Any questions there? Okay, let's just speak off the record for a second. If I was going to find the answer here, see how nice those are? They're already set up to graph. I could just graph the two. Wherever they meet, I'm already giving away a lesson for this week. We're going to graph and see where they meet. I have other strategies if graphing isn't the best strategy, because it won't be all the time. This one, these aren't ready to graph. You'd need to do a little work here to get them ready to graph, but then you could graph them. Don't do too much of that right now. Don't do, even though the question says find the hourly rate, don't do it yet. Let's just work our way into that. Let's be patient. Here's the other type of word problem that's going to drive us nuts this chapter. Ooh boy, if you've fallen asleep, wake up for this. A basketball coach bought 20 basketballs, some practice balls, and some official game balls. Apparently they were two different prices. Some cheap basketballs and some expensive basketballs. The coach's cost was a total of $700. If practice balls cost $30 each and official balls cost $50 each, how much of each did the coach buy? What are the two unknowns in the question? Yeah, what are how many of each ball? So let x equal number of practice balls. And let y equal number of official, and I'm going to put in brackets, game balls. Are you okay with that situation? Understanding that the practice balls are like those cheap rubberized ones. And the game balls are like, whoa, leather on the outside. You know, these are the ones we're going to use when we're actually competing. Now, friends, I don't expect you to completely get this example yet. This is what we got to work on this chapter, because this is difficult to come up with the two equations. X is the number of practice balls. Y is the number of game balls. What's the first piece of information I can use to come up with an equation? Do you see any piece of information that might help me come up with an equation? Oh, he ignored me. I was standing here staring at this one. He's going after the big equation, okay? He's going after the really big one. Might find it easier. He says 700 equals, how do we get to 700? What do you got to do? Say it again? Okay, so if a practice ball is $30, what do we got to do with the 30 to figure out how much money we spend on practice balls. How many practice balls is there? 30 times. X. That's the major breakthrough in algebra that some people never get to. They say, how many practice balls? Like, that's what I don't know. I'm like, I know, that's why we're using X. We don't know what X is. So what's the other part then? 50 Y. And let's just put a smiley face beside that, because if you get that equation, all this me talking about how things are going to get a little difficult here, you're like, not much more difficult than that. Okay, can we just talk about something? Like, doesn't the coach know how many balls you have? Can you just look in the bag? I'm like, that's absolutely true. Let me give a different question that's just like this one. Just like this one. That goes on every day in the chemistry lab here at the school. Let's say you want a solution that's 40% hydrochloric acid. I don't know if that's too high or not. I'd have to ask Mrs. Todd whether 40% is too high. But all she's got in her cupboard is 10% hydrochloric acid and 50% hydrochloric acid. How much should she use of each one to get 5 liters of 40% hydrochloric acid for the experiment she's going to do? It's the exact same question as this, but you got to know a whole bunch of chemistry. So please don't mistake, friends. Yes, no coach is doing this with the basketballs. They just open the bag up and count the basketballs. But we practice on ones like this so that when the chemistry questions come up, we're ready. Okay? That's the game in math. So don't be fooled by the easy questions we're doing that are ridiculous. That's what we're going to use to get ready. Okay? All that time to give you time to think about what the other equation could be. He dealt with the $700. What's the other number in the question I got to deal with? There's 20 basketballs. This equation's way easier. Number of practice balls is X. Number of game balls is Y. What do those two things have to add up to? 20. That's the hard part of this chapter, what we just did there. Everything else I'm going to show you is awesome algebraic techniques, but that's the part you might have a little bit of trouble with. So don't panic about that if that's a little bit much for you. Do you need more time? Well, to give it a little more hands-on feel, let's talk about it in an actual situation. Judy is considering 2 sales positions. Sam's store offers $1,600 a month plus 2.5% commission. Carol's store offers $1,000 a month plus 5% commission. Write an equation for Sam's offer and another one for Carol's offer. So here's the equations. Let Y equal money made. Let X equal sales. By the way, I had a job like this. I worked at FM Audio Video that worked a lot like this. This is exactly what I got paid. I got paid $125 per week, plus something in the neighborhood of 4% of whatever I sold. So 4% of the things I sold. So selling things decided my pay. So if you wanted the 2 equations here then, so this is Sam's store. The money made will be equal to $1,600 plus 2.5% of sales. How do I do 2.5% of something? What's 2.5% as a decimal? Oh, that's a shockingly tough question early on. 0.025. All I did there was take 2.5 and divide it by 100. So then Carol's will be Y equals, instead of Carol's you get $1,000 plus 0.05x. We've jumped right into a real world question here, friends. So that's A, made the equations. B, which one's the best for Judy? This one we can do. They told us how much Judy made in sales, so I can do both. So I can do, okay, Sam, Y equals 1,600 plus 0.025 times 15,000? And I can get that answer. I'll get that in my calculator in just a second. Oh, Sam. That was supposed to be a colon. And then, what's the other one? Carol. Y equals 1,000 plus 0.05 times 15,000. I'm going to type those both into my calculator, see what I get, and that'll help us decide where she should take her job. Let's see, 1,600 plus 0.025 times 15,000. If she works at Sam's, she'd make 1975. 1,000 plus 0.05 times 15,000, 1,750. Sam's is best for Judy. I just plug those in to find out which ones works better. Sort of makes sense. Sam's starts at 1,600, so it really looks like Sam's is going to be better. Can you imagine, though, that at some point, if she sells a lot of stuff, Carol's might get better because she's getting 5% of her sales. So it might get better. It will get better. But we'll talk more about that as the chapter goes along. Any questions there? Okay, more big ideas for the chapter coming. Do you need more time there? You okay? More big ideas for chapter. Example, the solution to a linear system is an ordered pair. In grade 9, when a point was on the line, we said it satisfies the line. We built on the same idea in grade 10. We build on the same idea. When a point is on the line, it's considered to be a solution. So this is -2, -3 a solution? Let me check. I encourage you to do left side, right side check. Even if last year you weren't doing left side, right side, you're going to want to, in grade 10, do left side, right side. And here's what left side, right side looks like. You put y over here, you put 3x plus 4 over there. I'm going to sub the numbers in and see if I get the same thing on both sides. See if it works out. So what's the y value? -3, put that in. What's the x value? So I put 3 times -2 plus 4, -6 plus 4, -2. Did I get the same thing? No. -2, -3 is not a solution. Now, listen, friends, let me introduce you to your new best friend. It's a program. It's a website. It's also a app that you can put on your phone, and it's called Desmos. Have you heard of it before? Desmos. Because I want you to see what just happened here. Who's got the thing on their page that can show me, can tell me? What was the equation? Y equals 3x plus 4. And what was the point? -3, -2? -2, -3. You see how good this program is? Yeah, you can quickly type this in and see what's going on. I know you don't have it on the test, but it's helpful for homework and seeing things. Do you see what's just happened? The point's not on the line. It didn't work out in the equation. That's what the example is trying to say, is that when you sub it in, you can algebraically see it's not on the line. Okay. Any questions on that? Okay, last example, which is good because we're almost out of time. We've got other things to take care of. This is what we're doing this chapter. Given any linear system, the solution is something that satisfies both equations. So I got to do it twice. I got to check y equals 2x plus 1 over here, and I got to check x plus 2y equals -8. So over here I do left side, right side. And again, if you haven't seen much of left side, right side, that's okay. I'm going to show it like a million, gabillion, zillion times this chapter. Let's check if this point's on the first line. So y is -3, x is -2, I hope you can do these steps yourself. If not, that's what you got to work on in the homework. Was the point on the first line? Yes, that worked. It's on the first line. Next, left side, right side on the other equation. This one's x plus 2y. This one's negative 8. Sub in the negative 2 as x and the negative 3 as y. And I get negative 8. Is the point on the second line? Yes. So this is a solution. Yes. Negative 2, negative 3 is a solution. That's the fancy word we use for it. But let's go back to Desmos. I'll come back to this. So if you need more time to copy, don't panic. I just want to show you Desmos really quick of these two equations. Desmos, Desmos, Desmos. Where was it? Who's with me? What was the first equation this time? 2x plus 1. And the second equation was? X plus 2y equals negative 8. X plus 2y equals negative 8. Did I copy that down right? And the point? Negative 3. Major breakthrough in our thinking right here, all on the graph there. If you graph those two lines, they both go through negative 2, negative 3. It gets better than that. There's only one point they both go through. That is the solution to these equations. Okay? Does your notes have a piece of graph paper there? I encourage you, in preparation for tomorrow's quiz, to see if you can go through the steps to graphing those two lines. Pretty easy. A little bit harder. Yes? So try those out to get ready for the quiz. Questions about that, though?